Namaskar and welcome to episode number 4 of Understanding Feynman's Physics podcast. Changing magnetic field produces electric field, and changing electric field produces magnetic field. Did you know that there is a constant c square that appears in the equation number 4 of Maxwell's 4 equations? C is the speed of light. It appears, according to Feynman, because magnetism is in reality a relativistic effect of electricity. Ooh. Magnetism is not real. It's a relativistic effect of electricity. I mean, it is real, but like real, not as real as electricity. No, I'm just kidding. I don't know exactly what it means. But it's fascinating to think about that magnetism is a relativistic effect of electricity. What do I know of relativity? Things appear to be shorter when they are moving close to the speed of light. Things appear to time goes slower when you are moving at almost the speed of light compared to the people who are not moving at speed of light. Although relativity shows that if you are moving at speed of light, it means that they are moving at speed of light compared to you. So how does that work? I knew this. I knew how that works when I was in college, first year of university physics, computer science course, first year, first semester, relativity and stuff like that. I remember doing equations, but I am rusty with equations now. So I decided that I'll just read what Feynman wrote and try to understand how it applies to the 4 equations of Maxwell. What are the experiments? What are the physical phenomena that are explained and that can be predicted by these 4 equations? The 4 equations, from my point of view, all I can tell about that is that the first equation says that in a closed surface there is a charge. If there is a charge, the flux would be proportional to the amount of charge. The second equation says that the closed surface, the magnetic flux is 0. We discussed that yesterday. You don't have to. The third equation says that a change in a magnetic field creates electric current. And the fourth equation says that the change in electric field creates magnetic current and stuff like that. So how does that affect our experiments and naturally occurring phenomena, right? So first things first, when you comb your hair, static electricity, you feel your hair attached to the comb. If you use a comb on your hair, and then you can pick up pieces of tiny paper from the table, right? That's because there is a charge there is a plane in the sky. So many planes we are having these days now. I don't know. Let it pass. When you comb your hair, some electrons are shed from either from your hair to the comb or the other way around, there is some charge. I have to look it up whether it's a positive charge or a negative charge on the comb, and that positive or negative charge can pick up the pieces of paper. Why? Because of this equation, that force the charges attract each other, right? The second experiment that is fascinating is, the overhanging wires, electric wires overhanging, like the ones we see on the road, a lot of them in India especially. There are wires hanging horizontally through delivering electricity to homes, right? If they imagine that wire, right, and you have a huge magnet underneath it with a strong magnetic field, and you face it up, as in the north pole is up, the south pole is down, which means there is a magnetic field going upwards. Okay, if the charge is going, if the current is going forward in the wire and the magnetic field is going upward, the the wire will move to the left. All right, the wire will move to the left. It's a left hand rule or something like that. I remember in college we made this, we used our thumb, index finger and middle finger, and put them all in of the left hand, and hold these four fingers, digits in right angles to each other. One finger showing the current, maybe the index finger, one finger portraying the magnetic field, maybe the thumb, and the middle finger would then show where the force is on the wire. All right, that's one experiment, right? But this is where I like Feynman. Okay, this is where I like his way of thinking. I really like it. I really dig it, and I want it. I want to embrace it and feel it in my own self. This is what this is what he says. When a current exists, he's talking about the same thing that I was talking about right now. The charges inside the wire are moving so they have a velocity v, and the magnetic field from the magnet exerts a force on them, which results in pushing the wire sideways. Another plane so quickly, another person on the door. Okay, anyway, so see, this is what I was talking about. When the wire is pushed to the left, we would expect that the magnet must feel a push to the right. Why? Otherwise, we could put the whole thing on a wagon and have a propulsion system that didn't conserve momentum. In trying to explain this phenomenon, he goes directly to the king of all principles of all physical principles, a conservation of momentum, which is a principle that has to always be followed, right? If there is a force on the wire, there has to be a force on the magnet. Otherwise, we can use it to create a perpetual motion machine, nothing short of that. That is the level of here it is attitude, like not I mean, why do I like it so much? Let me convey that fact. I like it because it's just so it's not like, oh, because the equations say so, or we found it out, or I don't know how else to say it. I don't know. Maybe I'm not conveying it properly, but I love it. I love that he goes directly to the the solidest principle in order to explain a phenomenon. Although the force is too small and whatnot, there is a force there, right? That's one experiment. Now, if there are two wires going, instead of one wire, there are two wires that are, if there are two wires and they at the overhead wires, and they have a current going through them in the same direction, the wires will attract, right? If the current is going opposite, the wires will repel. That's one. We don't see it happening in the real world, even though there is a lot of current, because of all, I think because of alternating current, maybe because the current is always changing. Maybe they also have some mechanism um, to allow for that and not create a catastrophe in the sky, I don't know. Maybe I'm one thing I'm conveying is my lack of confidence in in this physics. Still I'm trying. So there is this is what I find fascinating here. If you So there is this bar magnet that we just one wire overhead, there is a bar magnet in your hand, and you say that, okay, there is, you can actually remove the magnet and have a coil underneath, and have current going through that coil, which creates the magnetic field. This is the basis of all the electromagnets. You see electromagnets in motors and stuff like that. There is a coil, and if a large enough current goes through that coil, there is a magnetic field. And if we use alternating current, the current is changing, the magnetic field is also changing, and that's changing magnetic field creates current in some other wire. That's how the AC motor works, I think. All these phenomenon actually run the world. Electricity runs the world right now. Everything, electricity runs the world. The fact that we have computers is because of semiconductors, which are these strange material that sometimes conducts electricity, sometimes it doesn't. Very strange. But we can reliably determine when it does and when it doesn't, and that's all it takes to create a civilization of this scale. Very strange things. Just this magnetic phenomenon that runs the whole thing. So he says that we can understand magnets in terms of permanent currents in the atoms of iron. So this is what he's saying. In short, electric currents as well as magnets make magnetic fields, right? Both the coil and the magnet are creating magnetic fields. So it must mean that these magnets have a permanent electric current through them, which is creating these magnetic fields. The force. So he says, I'll just read it because he says it so nicely. I cannot just paraphrase it and assume that I understood everything. Where do the currents come from? One possibility would be from the motion of the he's talking about the currents inside the magnet. Where do these currents inside the magnets come from? One possibility would be from the motion of the electrons in atomic orbits. Actually, that is not the case for iron, although it is for some materials. Okay. In addition to moving around in an atom, an electron also spins on its axis, something like the spin of the earth. And it is the current from the spin that gives the magnetic field in iron. I mean, this is the case with all material. All the atoms in all the type of material have electrons that have a spin, right? But the point is, most of the substances, these electrons spin one way, some electrons spin one way, some spin the other way, so all the magnetism that is created just cancels out. But in iron, for a mysterious reason, he writes this, he's not shy about saying things that he doesn't know. This is the beauty of this guy. He doesn't care that you think that he doesn't know it. Nobody knows. For a mysterious reason, which we will discuss later. Oh, I think he knows. So because we were going to discuss later, I guess he knows. But he still says it like that. Many of the electrons are spinning with their axes lined up. And that is the source of the magnetism. Okay. So this is where we'll stop. Fascinating new discovery, actually not a discovery, but just a fascinating new understanding about iron in our lives. These iron, these ferromagnetic substances that attract magnets, these keys and these keychains and the big door bolt, the big iron that we iron our clothes with, the what else is made of iron in our lives? I guess that's it. Oh, my mic stand. My mic stand is ferromagnetic. These beautiful, abundant iron things. They have this amazing property that there is perpetual electric current going through them. How is not in normal iron, but in magnetic iron, where there is a magnetic current, the magnet found in nature. But I think in iron you can actually do it. If you put a magnet across iron for long, you can magnetize it. We would do that in childhood. There are ways to doing that. So there is a possibility, there is a potential in iron particles, iron things made of iron to have a perpetual electric current. How fascinating is that, right? See you tomorrow, or maybe day after tomorrow.